All right, so I've got a question here about some data that allegedly some biologists collected. So we're given a little table here, and I think that if I remember right, I was looking at this problem the other day. I think the numbers are a little bit screwy, but we'll give it a shot with how they wrote the problem in our wonderful textbook. So looks like this. Maybe I should have typed it out. Oh well. We're in too deep at this point. Okay, and so here we go. And it asks us to do log n, and that's just typing in using the log button on your calculator. So log 115, log 178, log 480. Let me write those in there. So this is what? 2.06, 2.25, 2.68, log 900, 2.95, log 1600, 3.20. Great. So nailed the first part. Now we're going to draw a graph of log n against t. So what that means is we're trying to graph on the y-axis is log n and on the x-axis is t. So let's say that this is 5, 10, 15, 20. This is obviously not going to be the most accurate graph you've ever seen, but here's log 1, log n equals 2, log n equals 3. So 3 is right about there. 5 is a little bit bigger. 10 is a little bit bigger. 15 is a little bit under 3. 20 is a little bit over 3. And when you look at that, it looks semi-linear. And this is one of the ideas of a logarithm, is that if your n value is increasing exponentially, it often just shoots off of your graph, and you can't see where it goes because it grows too big too quick. So if you, instead of making your y-axis just the raw number, if you make it the log of the number, a exponential graph now appears as a straight line. Beautiful. So what type of model? It looks semi-linear. So what we're going to do is try to come up with a model here of a y equals mx plus b model. But of course, what we're actually talking about is the y value. The y-axis was log n, and the x-axis was t, like this, mt plus b. And I could ask my calculator to do a regression, and that would be a good way to get it because these numbers, I could choose 2 points and use that to calculate the slope, or I could ask it to do a regression line. I'm going to do a regression line here. So remember, you press the stat button, then you hit enter, and you type your data in. So I'm going to type in my t values, and then I'm going to type in my log n values. Okay, so I got that all typed in there. I'm going to ask it to do a linear regression. So I hit, let me show you that again. I hit stat, then I hit the right arrow key, then option 4, right there, and then I hit enter. All of this stuff is ready to go, so I just hit enter a couple more times. Spits out this. Okay, so if you notice, when you look at this value down there, the r squared and the r value are pretty darn good. So that's great. So that means that log n is equal to 0.0669 t plus 1.919. And it says the r squared value is almost 1. That means this is a pretty darn good model. Now, of course, it's weird to say log n equals this, so I'm going to convert this to n. So I'm going to raise both sides as the power of 10. So what that means is now n equals 10 raised to the 0.0669t plus 1.919. Now you can simplify that by asking your calculator, what is 10 raised to the 0.0669? If you do that, you can see that number right there is the base of t. So n equals 1.1665 raised to the t. Now what do I do with the 1.919? I go 10 raised to the 1.919, and that gives me 82.9899. So I have 82.99 times 1.1665 to the t. And so that right there is an exponential model that that should model the data pretty well. So for example, if I go 82.99, 1.1665 raised to, pick a random t value from our table. Let's pick 5. When you do that, it tells me 179 in the table. For t equals 5, I should have 178. So my model's pretty good. If I run it again and try t equals 20, I get 1806, a little bit of an overshoot from 1600, but still not terrible. So this was the process of taking some exponential data and then making it linear by graphing it with a log scale and then finding the model from there. Let me know if you have any questions.